Okay, in this video we got 6.5 and 6.6. 6.5 is matrix products and inverses, and then 6.6 is, I don't know, more inverses? Well, applications of matrices. Applications of inverses. Okay, starting off with 6.5 matrix products. So in 6.4 we talked about adding and subtracting and multiplying by numbers called scalars. In 6.5 we talk about multiplying matrices. Before we get to that big topic, we have to think on the small scale. What does it mean to multiply a row and a column? First off, as it says there on the screen, we define a row matrix to be a matrix of one row. Likewise, a column matrix to be a matrix of one column. So for instance, if I had the matrix R to be 1, 3, -2, 6, and the column matrix C to be 6, 7, 0, 2. R is a row matrix because it has one row. C is a column matrix because it has one column. Now, a row matrix can have as many columns as it wants, and a column matrix can have as many rows as it wants. Notice our R is a 1 by 4, 1 row, 4 columns, and our C is a 4 by 1. Purposely did that way. And we can find their product, RC, and what that would do is, let me write this down. Let me copy these correctly next to each other. So if we multiply a row and a column, what has to happen is, this is my write this down voice, you have to multiply corresponding entries and add. Multiply corresponding entries and add. The benefit of the video is you can watch that 97 times. Extra credit if you watch it 97 times. You get 0.002 points. All right. What that means is you would multiply the first entries together, 1 times 6. The second entries together, 3 times 7. The third entries together, -2 and 0. And the fourth entries together, oh gosh, I ran out of shapes. We're going to go leaf shape. 6 and, oh, how do I draw this leaf? Do I put it on its side or do I go vertical? I didn't change the triangle, so I guess I have to go vertical. 6 and 2. So the product R times C would be 1 times 6 plus 3 times 7 plus -2 times 0 plus 6 times 2. So let's see, that's 6 plus 21 plus 0 plus 12, 39 I think that is. Yep. So notice when you multiply a row and a column, you get a number. Technically, it's a matrix. It happens to be a 1 by 1 matrix. 1 row, 1 column. But we can sort of treat that as just a number for our purposes. Okay, so to multiply a row and a column, you must have corresponding entries. Well, what made them corresponding entries? Well, R was a 1 by 4, and C was a 4 by 1. So what had to be true in order to multiply and have corresponding entries? Notice that is the number of columns of the first matrix must equal the number of rows of the second matrix. So let's back up, because you can rewind. In the previous video when we talked about adding and subtracting, the thing that must be true to add or subtract was the matrices had to be the same size. Done. Both m by n, whatever m and n are. To multiply two matrices, what must be true is the number of columns in the first must equal the number of rows in the second. Because remember, when we say m by n, the first number is row and the second number is column. row, column. Okay. So with that said, and let me prep this over here. There it is. Before we get to an example video, we have to talk a little bit more. Let's formally define matrix multiplication. Now, this definition is crazy, a lot of notation. It's going to be okay. Let A be an M by R matrix, and let B be an R by N matrix. Okay, stop there. Oh my gosh. So A is M by R, and B is R by N. Okay, so notice how many columns does A have? It has R columns. How many rows does B have? It has R rows. So notice the number of columns of A, I should say the number of columns of the first matrix is equal to the number of rows of the second matrix. Okay, so we satisfy the requirement that's built into this definition. You just have to be able to read it to say that you can multiply the matrices A and B. All right, now let's continue some more. Their product AB is an M by N matrix. Stop there. So if you can multiply two matrices A and B, as we have here, M by R and R by N, then the result called AB is the number of rows of the first by the number of columns of the second. Meaning if A was a 2 by 5 and B was a 5 by 7, the number of columns here matches the number of rows here. Check. That means the result will be a 2 by 7. Hooray. Okay. And before, I want to do this right now. And what if we switch these? What if B was first and A was second? Do the number of columns here match the number of rows here? No. So, is matrix multiplication commutative? Can you switch the order? No. Sometimes it works, but for the most part, it doesn't work. So unlike real numbers, where 2 times 3 is the same thing as 3 times 2, in matrix land, A times B does not have to equal B times A. In fact, one of them doesn't have to exist, like we're seeing right now. And even if you can switch them and go back and forth, you may not get the same answer. So we do not have commutativity. I almost stumbled on that word. I sort of still did. Okay, so let's continue with this definition. Where the ijth entry is found by multiplying the ith row of A and the jth column of B. Oh my gosh! Christmas came early! You're welcome, America! What does that mean? Well, let's talk about an example. We're going to go on this very small scale. So let's suppose that A was a 2 by 2. 2, 3, 6, 7. Awesome. And B was also a 2 by 2. 1, 2, 3, 4. Awesomer. Now, again, do not think, oh, they're the same size, I can multiply them. Same size is referring to adding and subtracting. 2 by 2 times a 2 by 2. You can also multiply, but it's for the rule of the number of columns here matches the number of rows here. Stop. That's the only thing you check. The result is going to be the number of rows here by the number of columns here. So the result happens to also be a 2 by 2. Now, this is the large print edition on purpose. Okay, so let's talk about what this definition is saying. Let's suppose we want to find this entry here. Which row is that entry in? Notice you would say it's the first row. Which column is that entry in? It's the first column. So now let's replace this. Where the 1, 1 entry is found by multiplying the first row of A by the first column of B. That's what that means. So we're going to multiply this row by this column. How do you multiply a row and a column? I'm going to go back a slide. To multiply a row and a column, what do? We multiplied corresponding entries and added. So that first entry would be 2 times 1 plus 3 times 3. 2 times 1 is 2, plus 3 times 3 is 9. 2 plus 9 is 11. Excellent. Let's try another one. Boop. Let's find this entry here. What row is it in? It's in the first row. What column is it in? It's in the second column. So to find the 1, 2 entry, we multiply the first row of A by now the second column of B. So first row, second column. So that's going to look like 2 times 2, multiplying corresponding entries, plus and adding 3 times 4. 4 plus 12, 16. And then we continue. I don't want to do too much in this video because I have some examples for you. So just to skip ahead, if we wanted to find this entry here, what row is it in? It's in the second row. What column is it in? It's in the second column. So we would multiply the second row of the first matrix by the second column of the second matrix. Multiply corresponding entries and add. Comment. You can totally do it by hand if you really want to. Or you could use your calculator, to be very honest. There's really no way for me to check if you used a calculator or not for matrix multiplication. And the reason being is because I don't need to see this work off to the side. I don't need to see you writing 2 times 1 plus 3 times 3. That's completely up to you. Here, this is at the smaller scale. We're only working with 2 numbers at a time, 2 pairs of numbers, I should say. If you had like a 5 by 7 and a 7 by 20, don't do that by hand because you'd be multiplying and adding a bunch of times, and you don't have time for that. So if that were the case, definitely calculator. Now, in the video that you're going to watch, I'm pretty sure I show you how to do it by hand and then also by calculator. And that answer is, yeah, I do. I do show you how to do both. Okay. So if you would, please watch video number 77. Is that correct? Yep. 77, and then also watch video 78. So 77 is just matrix multiplication like this. 78 is an application of matrix multiplication. So similar thing as before. This does actually have real life use. But again, in real life, you'd be using a computer to do it all. You wouldn't be doing it by hand. All right, so watch those 2 videos, 77, 78, and then come on back. Okay, so before we get to this, the second half of this section, we have to talk about a very important matrix. I don't know where I'm going to put it. I'm going to put it right here. Okay, and it's called the identity matrix. The identity matrix is a matrix, really, that acts like the number 1. The identity matrix is a square matrix. Square means it has the same number of rows as it does columns. So this is the 2 by 2 identity matrix, which we would write as capital I sub 2. And then we have the 3 by 3 identity matrix, I sub 3, and then that can be as big as it wants to. But it's always a square matrix, the same number of rows as it has columns. So this matrix acts like the number 1. So if we took any matrix, 1, 2, 3, 4, and we multiplied it by the same size identity matrix, and you can check this, you would get the original matrix back. So the reason I say it multiplies by 1 is 5 times 1 is 5. Same deal here. Any matrix times any matrix is that first matrix again. And this goes in either direction. So if the identity matrix was first, oh my God, Marsh, you're going to town on that toy. I'm really sorry if that's really obnoxious. But he's having a good time. That's what's important. Even if you switch the order here, here is where commutativity is okay. But in most cases, it's not. Okay, so why is that identity matrix so important? Because now we can talk about inverses. So there's two types of inverses that we're going to deal with in class. Well, actually, just the one type. And that's called the multiplicative inverse. In a real number scenario, what you're already used to, you know that 5 times 1/5 gives you 1, and 1/5 times 5 gives you 1. So we would call 5 and 1/5 multiplicative inverses of each other because they get you back to 1. So is there multiplicative inverses in matrices? The answer is yes, sometimes. And it's one matrix is the inverse of another matrix is when you multiply them, you get the identity matrix, because remember that guy acts like the number 1. So with that said, let's go to the definition of a matrix inverse. The n by n matrix, stop there. Remember, when it's n by n, that means it's a square matrix. Same number of rows as it has columns. Is said to have an inverse, denoted, that notation is pronounced A inverse. You don't say it as A to the negative 1. It does not mean the reciprocal of A. It means A inverse. Just like if you ever had a function inverse, that's what that meant, F inverse. The inverse is also n by n, so another square matrix, provided that, and what this says in notation is if you have the original matrix and the inverse and you multiply them in either direction, you always get the identity matrix, which again acts like the number 1. So this is what an inverse is. It undoes the original matrix. Just to note, if a matrix doesn't have an inverse, we call it singular. There it is, singular. That's a matrix that does not have an inverse. A matrix that does have an inverse is called non-singular. Hooray. So everyone on Tinder is singular, hopefully. And everyone not on Tinder could still be singular, or there could be non-singular. Horrible joke. You're welcome. I'll work on it later. At least I'm not wearing pajamas. Anyways, now let's talk about how do we find matrix inverses. Well, it's a process. And this is where Gauss-Jordan comes back to say, I know. And what you do is to find a matrix inverse, you take your given matrix, I really hate this sometimes. You take your given matrix A and you augment it, remember augment means to make bigger, with the same size identity matrix. So that's step 1, is take your initial matrix and augment it with the same size identity matrix. Step 2 is to use Gauss-Jordan so that the identity matrix appears on the left-hand side. So your 1s and your 0s. And I forgot to mention, we saw the 1s and 0s earlier in section 6.2, 6.3. Yeah, both of those sections. Because that was the 1s and 0s we wanted. That was our goal. That's what we called it. So step 2, after this augmentation, get the identity matrix on the left. If you are able to do that, because it's not guaranteed, you're not guaranteed to have an inverse, then the inverse will appear on the right. So that's step 3. So for example, if I had the matrix 2, 3, 6, 7 as my starting matrix, I would take that matrix 2, 3, 6, 7 and I would augment it with the same size identity matrix 1, 0, 0, 1. And then I would use Gauss-Jordan to get the goal on the left-hand side And if I did that, then I would have 4 numbers there, most likely. In this case, yes, it does have an inverse. And those 4 numbers would be the inverse of the original matrix. So for example, where this 2 is at, you would want a 1. And then after you make your 1, you would make your 0. So you can say -6 times the first row added to the second row gives you the second row. And you repeat everything you've been doing in 6.2 and 6.3. Okay, so I have 2 examples for you. There's a 2 by 2 example, and then there's a 2 by 3 example. I'm sorry, 3 by 3 example. Now, also in this video, I think this is where I teach you how to use the elementary row operations in your calculator. I can't remember if that was done earlier or not, but this might be the video that I do it in. For this to be good, you have to make sure that your 6.2, 6.3 stuff is great. You can do all of this by hand if you want to. It's going to be highly recommended that you learn how to do the elementary row operations in the calculator. Because when we get to larger matrices in Chapter 7, it saves you a lot of time, especially when there's fractions involved, and there's going to be fractions involved. So if you would, please make sure 6.2, 6.3 is great before you watch this next video, which is video number 79, which has 2 examples, and that should put you at the end of 6.5. Come on back, and then we'll do 6.6. Okay, so now we're in section 6.6. Now, 6.6, we're not going to do the entire section. We're only going to do the first part of it, and that's using a matrix inverse to solve a system. So you now will have 3 ways to solve a system. You'll have elimination method, you'll have Gauss-Jordan, and the third way is Gauss-Jordan with matrix inverses. So those would be your third way. There's many other ways, but these are usually the big ones that we teach in this class. Okay, to use a matrix inverse, let's go back to a system of equations itself. Suppose we had 2x plus 3y equals 9 and negative x plus 5y equals 12. Okay. Well, actually, let me go backwards. Well, no. You know, I can tell you this way right now. A system of equations we learned in 6.2 can be represented as an augmented matrix, where you have the coefficients and then you augment the constants. Great. That worked in 6.2, no problem. In 6.6, we can also treat a system of equation as an equation of matrices, where you have a coefficient matrix times a variable matrix, and that equals a constant matrix. So our coefficients were 2, 3, -1, 5. Our variables are x, y, and our constants are 9, 12. The reason this works is because, remember, if you take the first row and multiply it by the first column, you get 2 times x plus 3 times y. Well, that makes 2x plus 3y. And then that would equal 9, because the 1, 1 entry on the product would equal the 1, 1 entry on the right-hand side. And same thing for the second part there. I'm going to erase all that stuff because I don't want that in the way. Okay, so every system of equations could also be thought of as a matrix equation. Okay, so with that said, how would you solve a matrix equation, you ask out loud as a good student? And I say the same way you solve a linear equation. So if I had the equation 3x equals 5 and I said solve for x, and you're only allowed to use multiplication, because I didn't say this earlier, well, I mentioned it, there is no division for matrices. We don't know what that means. We only can do multiplication. Then you would say, oh, I would multiply both sides by 1/3. Because 1/3 and 3 are inverses of each other on your multiplication. So when they multiply, you just get 1, and 1 times x is just x. So on the other side, you'd have 5/3. All right, so same deal here. You would take the inverse of the coefficient. So the inverse of the coefficient, we would have to find. Let's just call that A inverse. And you would multiply both sides by A inverse. So by design, these two would just cancel out, which means your variables, x, y, just like how we had x here, would be equal to the inverse of the coefficients times the constants, 9, 12. So just like here, we had 1/3 times 5. We can call that 5/3. So that is how you solve a system using a matrix inverse. Inverse of the coefficients times the constants. So this kind of problem's got everything. It's got your Gauss-Jordan, because you have to use that to find the inverse of a matrix like you did in the previous video. It's got matrix multiplication, which we had to do in I don't know anymore, 4. I'm going to say 4. It feels good. It's got converting a system of equations into matrices. I love it. I love it a lot. Coughing. I'm coughing so much. Okay. So with that, we've got a video of using a matrix to solve a system. It's video number 80. So if you could watch video number 80, and then let me just make a comment. Yep. So this is another video to where I have you write it down, but then use the calculator to use the computations. Comment. What I'm writing down is what you still need to write down. Do not just throw this into your calculator and do some command to solve the system. Because if this were on a test, I would be asking for your work, cough, cough, and using the calculator to get the answer for the stuff is 0 credit. So FYI, you need to know how to do this, because otherwise you won't be able to get through Chapter 7 at all. Okay, so watch video 80, and that completes Chapter 6. If you have questions, you know who to ask. Boop, boop. Ciao.